Welcome everyone today at the Relatorium seminar. Today we have Professor Bob Coecke for giving us a presentation on his string diagrammatic formalism for categorical quantum mechanics. And what's better, it's not for graduate students, not just for but also for school students and kindergarten, even better. So he's going to talk about that today. I just want to add that when I started my PhD, I was struggling with category theory for 2 years, and it was the string diagrammatic formalism founded by Professor Bob Coecke and others. It helped me really click with the subject, and I finished my thesis. So thanks, Bob, for that. And just to introduce Bob, Bob is a visiting professor at the University of Oxford. He's a physicist, artist, and a mathematician. He's also a founding father of many research communities, including applied category theory and categorical quantum mechanics. And he's also a visiting professor at the
QPL, you forget
distinguished.
QPL, which you regularly attend.
Oh yeah, quantum physics and logic. That's right. Actually, this talk comes out of Quantum Physics and Logic conference. So I heard Bob speaking about this at the conference, and I was so excited that we should make this talk available at Relatorium. So here we have Bob. And one last thing I want to add is that Bob is also an artist. He is a pioneer of industrial metal band. He started playing music in the 80s. And his latest work, Quantum Guitar, is very cool. And people who want to check on that, please check his YouTube channel. He has a very cute tutorial on quantum guitar. So yeah,
Thank
let's
you.
open the floor to Bob. And here we are. Thank
Thank
you.
you, Priya. So I'm just gonna share my slides now. Share. Okay, that's the one. Share. Hope is that all good? And now I'm gonna do enter full screen. Oh, wait, enter full screen. Okay, that's good. Okay, good. So hello everybody. It's good to be here. So I'm gonna talk. I'm gonna talk basically about a diagrammatic formalism for quantum mechanics, which we are pushing very hard now as an educational tool. I understand that the idea of this conference series, Compassionate Mathematics, is to make mathematics not too hard and make it like as approachable as possible. And that's one of the things I've actually been doing for more than 20 years now, like following that sort of ideas. And in the past couple of years, this has culminated in something I think with a lot of potential. Well, I mean, it's up to you to judge that. But I'm going to start, well, very early on with the idea of the language of quantum. So this is going to be a talk mostly about quantum mechanics, but a lot of the material I present has been meanwhile adopted in many other fields. Like it's now very prominent in computer science too. It has become really prominent in mathematics for quite a while. There's a few Fields medals around like diagrammatic methods in pure mathematics too, for like by people like von Jones and oh, come on, another mate of mine. I just can't come up with his name. It's not okay. But even a lot of that mathematics these people were talking about all goes back to the origins of the language of quantum mechanics, by the way. Voevodsky, sorry, that was the name I was looking for, Voevodsky. It actually has quite similar origins, so even the path towards these developments, like the work of von Jones in pure mathematics and Voevodsky in pure mathematics, kind of follows to some extent the line of my talk here, at least aspects of it. So the language of quantum is due to John von Neumann, who people may know about from game theory, and is also the father of the modern computer architecture, which we all use, and many other things. I mean, many people consider him as one of the smartest people, if not the smartest person of the previous century, because he did so many different things at so many different levels. He was not just like pure mathematics, also super applied stuff, technology development, lots of stuff. Now, So von Neumann is the father of quantum mechanics in the sense that he published. So it's kind of interesting, just as an aside, that people say, okay, it's 100 years of quantum now, but it's because of Heisenberg, but it's kind of an ad hoc choice because people thought it's probably now the right time to say it's 100 years of quantum mechanics, but there could be so many other points in time that people could have decided, well, it's 100 years of quantum mechanics. I mean, I would say 100 years of quantum mechanics as like a matured field with its proper formalism was von Neumann. There is no particular one point in time you could say that von Neumann finished it, because he contributed things like density matrices and many other things gradually. But in 1932, he published a book which released the standard of the formalism of quantum mechanics, 1932. So that's when the first book came out, which has everything that people now use when doing quantum mechanics. Everything was there for the first time. And most of it was invented by him. Now, a very interesting thing, remember the date, 1932, was that in 1935, von Neumann said, I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. Hilbert space being the language in which quantum mechanics is formulated, relative to which quantum mechanics is not Hilbert space. It's sort of the backbone to formulating quantum mechanics. That's how you should think about it. And so 3 years after he published that book, he denounced his own formalism, which pretty much everybody is still using. So it's a very interesting fact. So from then on, there was some sort of quest as, can we come up with a new language for quantum mechanics? And when I say language, I mean not just like a way to represent, I also mean a way to reason in, like in which you do everything in. You reason, you do everything in it. You basically, the quantum mechanics sort of, it's the incarnation of the whole thing about quantum mechanics and what you can learn from it, how do you derive things and all of that. That's what I mean by language. So it's language in not just a descriptive way, but a lot more. And I'll explain more about that later. Okay. So this is Erwin Schrödinger, who you may know from his cat or from his equation. But also in 1935, the same year, Schrödinger said, when two systems of which we know the states by their blah, 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 enter into temporary physical interaction. Now, that just means there are two systems. It doesn't mean anything more for me. There are two systems together. It's not a system alone, it's two systems together. That's what it means. I would not call, so whatever happens then in quantum mechanics, Schrödinger would not call one, but rather the characteristic trait of quantum mechanics. So what happens when you put two things together? The sort of way your language needs to adapt to saying stuff about that. That's what Schrödinger thought was the most important thing. This went against like a little bit von Neumann, whose opinion was, and I think most people think, that the important thing about quantum mechanics, which really makes it different from how we experience our usual world, is that for von Neumann it was what happens if you observe a system. A single system, you observe it, and the behavior then is what characterizes quantum mechanics. Schrödinger said, no, it's just you put two systems together, and the way you have to adjust your language is the most important thing. Okay. Roger Penrose, here in Oxford, I'm at the moment here in Oxford. I mean, I've been based in Oxford 25 years, and at some point in the past, Priyaa spent 6 months here in my group at Oxford when you were still an MSc student, I believe. Yeah. So, okay, so this is Roger Penrose here in the Mathematical Institute in Oxford. You know of black holes, of course, and maybe of his connection with Escher and the paintings of Escher. So one thing that Roger did, like when he was still an undergraduate student and had to work with tensor notation, like you see here on the left, and these pictures on the left, is that he really didn't like it, and especially didn't like computing with them, like contracting them, putting them together in expressions. He really didn't like that. And then he realized that you can actually replace them with the blobs you see on the right. I mean, you see here, you take your tensor symbol, you represent by a blob. You take your subscripts and then you consider them as input wires to that blob. Then you consider your superscripts and you consider them to output wires to that blob. And he developed a whole like framework to deal with relativity and some other stuff, specifically with these blobs. He did this for himself. This was never really publicized properly or anything like that. He did this for himself to aid himself to studying these subjects. He felt this was a nice informal aid to do your calculations, just like Feynman diagrams or an aid to help you with calculations. Now, so von Neumann wanted a new quantum formalism. Schrödinger said quantum is about composing stuff. Penrose uses pictures instead of symbols. Well, the last two turn out to be one and the same thing. So if you use pictures a la Penrose instead of symbols, and I will explain this later, this is really about considering having more than one system together and doing stuff with it as your like principal actors of your theory, language, whatever. So that's sort of the main story about like this little bit of history. Okay, so here's first kindergarten quantum mechanics. So that's what the title refers to here. This is a paper I put out in 2005, in which, after some work with Samson Abramsky, well, not some work, like important work, but with Samson Abramsky, in which we start to axiomatize quantum mechanics in a compositional way, I realized, not knowing about the Penrose stuff because it was so hidden, that you could actually do everything, well, a good chunk of stuff in quantum mechanics with pictures and diagrams. Pictures and diagram. And I took this to be one of the driving forces for a lot of work that I did later. And then some 10, 12 years later, Alex Kissinger and I, we published this book, Picturing Quantum Processes, which was basically the textbook of quantum computing at Oxford, which I was teaching since 2012 till 2020 or something like that. And these were the course notes. So this is a full-blown course in quantum. I mean, you have to specify what quantum. Quantum, say, quantum theory, quantum foundations, quantum computing. And so everything is in there, quantum algorithms, like lots and lots of stuff. We derive the Hilbert space formalism from the pictures in this book. It's quite a substantial book, but I mean, we taught it in like 20 to 24 hours as a course at Oxford, which typically takes 8 weeks. That's just the format there. And so this was the textbook. But it was designed for like university students. It was designed for university students. Now, more recently, I think 2022, 2023, Stefano Goggioso and I, we wrote this book, Quantum in Pictures. Now, we already had the book Picturing Quantum Processes, so we had to carefully come up with a new title, which was not exactly the same, but it was hard to not kind of be similar in content. But still, this book is somewhat different. In a way, it covers exactly the same ground. There's one big difference, and that's it here. Hello, want to learn some quantum? Maybe you think you don't know enough maths. Well, that's not the problem. The pictures in this book are a new kind of maths that will teach you all about the quantum world. So basically, we got rid of mathematical prerequisites, the typical mathematical prerequisite, which you have about complex linear algebra, complex multilinear algebra, because that's where the tensor product lives and things like that. We got rid of all these mathematical prerequisites by basically teaching everything directly just in a language of pictures, which everybody can understand. Now, very important here is, of course, that it's a different kind of math. It's a different representation of math, a different foundation of math, even if you want. But it's very rigorous, proper mathematics. Very rigorous, proper mathematics. And right, so I'll say something more about this. First, I'm going to show. I mean, I'm trained as a physicist. So For many, many years, I didn't do any experiment. So I said, okay, it's time to do an experiment. So we did an experiment. And I mean, that's why there was this article in The Guardian which says, physicist Bob Coecke, it's easier to convince kids than adults about quantum mechanics. Again, come back to that claim. But so what we did, and this was a full page in The Guardian, by the way, December 2023. So we must have done something. So what did we do? We did an experiment, like a physicist should do. Like, well, I mean, I love pure mathematics and all of that, but I also like the idea that things can be demonstratable, like that you make a claim and then you demonstrate something. Well, I mean, one shouldn't forget, like, some of the origins of the purest mathematics we have, like Euclid, came from physical observation, and was in a way verifiable. That's a story in its own right. So where mathematics went, how it's connected with reality or not, that's a different story. Not going to go into that. So first, okay, we wrote this book, and the initial motivation for me to write this book was actually for this particular experiment we had in mind. So here you got a book, think of it as a textbook of a course. Think of it as a textbook for a course. Okay, so then we took the book and we created a whole bunch of videos. Think of them as lectures for a course. They basically cover the whole book. They were video lectures, but so think of them as the lectures of the course. Now, a course usually has exercises too, so we created some videos about exercises. Think of them as the exercises of a course. You maybe get an exercise sheet, you have to take it home, and then with a tutor, you go through the solutions, something like that. Okay, so all together, these three ingredients, they form the course. In not just a book, but a course. So we got a textbook, we got lectures, we got exercises. So then we send out this flyer only in the UK, and the reason we only did this in the UK was for reasons of ethical approval, given legal constraints. It's super complicated to do an experiment with, and I'll say it now, minors. Very difficult to do that, especially if, I mean, you need to get personal clearances and things like that. It's quite complicated. To do this in different countries is virtually impossible, except if you go to countries where nobody cares about this ethical stuff, which we're actually doing now. It just makes things like in Africa and which makes things much more easy because they don't worry about these things. Anyway, we are approved by the UK ethical standards, so we're not doing anything illegal. So basically send the flyer out and we asked people, hey, do you want to get a free course taught by people from Oxford University, Continuum, IBM involved. So it looked fair, and we're going to do it like in the summer. So if you are interested to use your summertime to do something like this, just apply. When you complete the course, you get a certificate. The way the UK system works to go to the university, it's very important to get as much as possible on your CV. So this would be very helpful for these people on their CV to just have this certificate that have taken a quantum course. We got about 1,000 applications. We tried to randomly select, because it was impossible to manage, of course, 1,000 people. We tried to as much random as we could select some 70 students, because we wanted to give some feedback, tutorial feedback on exercises, and so that takes time, that takes tutor, so that's all we could do. And we tried to select them random in the sense that we asked people whether they were mostly interested in science or humanities. We asked people how confident they were with their performance, where they were performing top of the class or not, and which school do you go to? You go state school or private school, and things like that, to make ethnical backgrounds, to make as, of course, gender, to make as random mix as possible as we could. Okay, so we
Bob,
gave.
if I may interrupt, like
Of
how long
course,
did it take? Thank you. How long did it take for you to set up this experiment, like with all the legal clearances, like
the
lectures,
legal
like
clearance took a year.
wow, okay.
Legal clearance took a year, and you can't. So you need an entity who has like the body or the department to be able to do this sort of legal clearances. So we used Oxford University, and it took a year.
Wow, that's a
Because
long
of the
time.
bureaucratic delays and stuff like that. And we were in
Mm.
the Department of Computer Science, which actually wasn't that familiar with these sort of things. If you're in a psychology department or I mean, like institutes which work with animals, then of course they're much more familiar with this. It was much more complicated to do this in the computer science department, which never had like anything like that going on. And
Right.
and I mean, even Oxford as a whole had not that much experience with like working with minors in such an experiment like this. I mean, the thing is, you have to realize, okay, we're going to teach quantum mechanics to minors. Are we going to traumatize these kids? No, it's a valid question. If they all
Yeah.
if they all fail, is this going to have a negative impact on their future, on their confidence? It's not. I mean, if you're going to say we're going to, well, if it's about like feedback on high school courses, that's a different thing. If you're going to say we're going to teach kids quantum mechanics, and then I mean,
Yeah.
that could have psychological impacts if it
This is
doesn't work out.
out of convention.
So it was a new thing, so it took a long time.
Okay.
Anyway, one thing, of course, we didn't say on the flyer, and the whole point of which was the whole point of the experiments. The point of the experiment, I mean, it wouldn't be an experiment to teach like well, I mean, it could be an experiment, and then you ask for some feedback and stuff like that. But we want to prove something much stronger. So essentially, at the end of the course, we asked them, hey, just to give some feedback to us. We presented it like that. This is for you to give feedback to us. This is not us testing you. We're going to give you a few exercises. Please try to solve them if you can. And then that would be very valuable feedback for us. So we gave them a bunch of exercises. So what, of course, I vaguely hinted at before, is that the course took 8 weeks. We followed exactly the structure of an Oxford University postgraduate course, on the nose. That's the 8 weeks, 8 weeks of lectures, weekly tutorials, like exercise sheets. We completely copied that. It was online, well, usually they're in person, but we completely copied that. And basically, the questions all came from Oxford University postgraduate exams in quantum, translated into the picture language, which of course we didn't say, otherwise they wouldn't even have attempted. Otherwise they wouldn't have attempted. And in the end, 50% of these students got distinctions. I think there was about 60 who finished the course. 10 dropped out for various reasons. But there was about 60 who finished the course, and half of them more or less got like a distinction, which is a hell of a lot more than I was expecting. I hope that some would pass. So it was much more than I expected. And that's what was reported in the Guardian article, which anyway, so here's some data. I think this is very relevant to the seminar. So the prior knowledge of quantum was mostly nothing or limited or moderate, so not so much. How much time did you spend per week? I mean, it's very hard to, that's the low, yeah, it's very hard to imagine that 1 to 2 weeks really mean that they only, 1 to 2 hours really means that they only spend 1 to 2 hours, because there wouldn't be enough time to basically watch the videos and attend the tutorial. So I assume this is on top of the obligatory. I think that's the time on top of what they were supposed to do anyway, I assume. But it's remarkable how little it is still. Table right top. The core strength, my motivation and confidence, majority agreed, which was nice, because there was all these ethical fears that they would all get like depressed and and negative. No, it had the other effect. It had the other effect.
That's awesome.
And then on the right, the course motivated my pursuit, me to pursue a STEM career. Again, a majority said yes. A
I
big
think it's great.
yeah. One thing which, okay, one thing which is not here on the slide, is we had some open questions like what did excite you the most, or what did you feel what about the course? I can't remember the formulation or something like that.
Mm-hmm.
The answer was not interesting. The answer was fun.
Great. That's awesome. That's awesome. That speaks for it all. Yeah.
Yeah, I mean, one thing I didn't mention yet is the last table. It shows that whether you came from a state school or the grammar school or boarding and private school, wasn't much different. All around 60% average score, which is interesting. Oh, one thing also I didn't say yet, which is I think subject to further research. The 15-year-olds did better than the 17-year-olds.
Oh, so the younger they are, they did better.
Huh?
The younger they are, they did better in the course.
Yes.
Is it that the 17-year-olds might have already seen some physics in school that would have corrupted their minds in some sense?
I think it has more to do with the maths than the physics even.
Okay.
I think their mind is already more sort of molded towards the way maths is typically taught. And then this would be a whole philosophical debate. Maths is typically taught like in a reductionist way, that you understand a thing from how it's made up. That's the whole point of set theory and things like that. And all Western sciences start like that. You think in terms of how a thing is made up. If you understand something, you understand the parts. This is true in biology, both in anatomy and both in like genetics. It's true in mathematics. This is true in physics with particle physics and things like that. That's a particular way of scientific thinking. These
Would
pictures I'm
would
going
you
to show, yeah?
would you elaborate on that a bit more, Bob? Like the reductionist way of how
Well, it's probably better to pick this up later after I present a bit more.
okay,
So that we're
yes.
not talking in the blue, because you know what I'm talking about, maybe some other but yeah, I'm happy to do that, like very happy. So
That
we can pick this up later. So the main thing I want to say is that now, just as a little advance, that the language in which I'm going to present the pictures, they're not reductionist in the sense that you understand the thing by how it's made up. You understand the thing by how it relates to other stuff.
Right.
And
May I sorry, Bob. May I just say, I'm glad you just said that. I think it probably would be useful to even underline that this is exactly what you meant by non-reductionist, because sometimes that term is thrown around to mean a vague set of things. But what you just said was very important, that you're proposing to understand the interactions, they understand the things through the ways they interact and connect with other things, rather than by asking, well, what is it? For example, when to ask what is a qubit, as I'm sure you're going to tell us, you're going to talk about qubits, it's pointless. You're missing the point. It's not about what it is, but it's how it acts, what it does with other things. And this is
with
a
other ones.
mathematical,
And
this is a
that's why
mathematical
and
perspective.
then that
Yeah.
goes back to what Schrödinger intended to what Schrödinger said. It's when you bring two things together that what you get is like the relationships between those two things which start to matter. Now, traditionally, people would think that's much more complicated to describe. What this story is about, this talks about, it's no, and it's not harder to understand. It's in a way more natural to understand. And the younger you are, the more you think still in those terms. So this could be a conversation about like developmental psychology too. More work needs to be done because the developmental psychologists have never looked into this properly, with some exceptions. Like Piaget did a little bit in that direction, and René Thom, who was actually a pure mathematician of the catastrophe theory, he actually had a lot of interest in education, and he made these claims too. And there is, okay, it is something we can go on discussion, but I mean, maybe it's a good thing that I pointed this out now. So thanks, Priyaa and Ted. Hey, let's go on. I mean, at the moment, lots of stuff is going on around the world as much as we can, because we're seriously understaffed and we need much more help. One of the highlights is that in Greece, they already last year taught this language in undergraduate in high schools. That's why basically they pushed the publication. We didn't even do that. The publication, they did it. They pushed the publication of a translation in Greece, which then could be used as a textbook for students in a high school in Greece to learn quantum. So the Greeks were very, very fast
Nice.
with this, which I'm sure Ted finds very surprising.
Well, actually, I know some of
every
those
Greek I
people.
know, they don't believe this.
No. I know some of those people. As you know, I know Andreas, for example, who
Oh, you know
was one of
Andreas,
the
yes, of
students.
course.
Yeah. And just incidentally, again, we'll continue talking about this later. But I'm adopting this. I'm teaching in a high school level, as you know, a QIC class in the spring, every spring, and I'm adopting this for next version for next spring. So I'm very much
Okay, thank you. So yeah, I mean, just for historical reason, I mean, it's interesting to see how these things go. There is a person, English, Johannes Antoniou, who used to be the head of the Solvay Institute in Brussels at some point. Solvay Institute, people know from all these pictures with Einstein and all these famous quantum physicists in Brussels. And he was for a long time like the second to Prigozhin, the Nobel Prize winner for like chaos theory and all of that. And then at some point he went back to Greece, but of course he's a very high profile, powerful person. And that's basically how this happened in Greece. And he was an examiner of my PhD. So I knew him very well. And he was kind of in the same, so he was the Francophone side of the same university where I was in the Flemish side in Brussels. So it was just a coincidence of somebody in the right place to get this through. That's kind
Small
of
world. Small world, right?
That's how it happens. That's how it happens. I hadn't seen him in like 20 years when he contacted me or something. And then yeah. Okay. So if you want, I mean, we have a paper out about this experiment. You can find this on the archive. As you can see, lots and lots of people were involved. So this on the archive. And a new, much shorter, this is a very big paper, 100 pages. Lots of experimental details. A much shorter one will possibly be put on the archive next week or the week after, which is much like a lighter read. Okay, let's start with it. So the basis of this language is the idea that a system is represented by a wire. So you already see there's sort of a departure of the typical, I mean, I didn't mention the word yet, but Parmenides. We can later go in all ancient Greek philosophy. Parmenides versus Heraclitus. This is much more already an Heraclitean perspective than a Parmenidean perspective. You don't represent a system by a point particle in space-time like Newton. You represent it as something going on. The wire is where it's happening, where it's moving into. I mean, this is like flowcharts, but there is a different philosophy already going on. And then one of these boxes means what you're doing to a system. You're changing it. It's the changes you impose as like first order, first class citizen, rather than where it is. Okay, now what you do is you just plug them together. And interestingly, what do you see here? You see two wires side by side. It means there is two things at the same time. I've got two things. That's Schrödinger. So without saying anything, without specifying anything, just at this very basic level of language, you got the idea that there can be two systems together as a first-class citizen. From the very outset on. So the whole idea about relationships and stuff like that is already going on here. Because when you bring two systems into a box, you're imposing a relationship between them. And you see, it's not complicated mathematics to say this. Like, I mean, I should have a picture like here. When the two things go in the spade, they're being imposed on each other. A relationship is being imposed. So this is all about relationships. That's all you're saying. We are not saying what's inside the wire. We're not saying that. We're saying when relationships are imposed between things in this picture.
In fact, sorry again to interject here. I think this is essential, and it is missed by many people who first study this. That the whole point is you're never saying what's in the wires. You never say what the wires carry. It's how they're brought together and what happens to them.
Yes,
Right?
yes, and I mean, and of course, the more mathematics you're Western style mathematics and physics and science, you've been educated, you lose thinking like that. Now, if you look at how we humans interact, it's like this. It's not about how you're made up. Like our life is about the interact. If you tell a story about your life, you say, okay, then I met this person, then I fell out with this person, blah, blah, blah. It's stuff like that. I mean, of course, this impacts your psychology. So there are the people who would basically say, how was your life? First, I was depressed. Then I was very happy. And then you start thinking, that person must have led a very isolated life. Versus the story, okay, then I went to play football with these people and then blah, 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 blah. That's our lives.
That sounds natural.
That's how we naturally are as humans. Like, if you ask, I mean, how do you describe a kid? Well, you describe it by its parents typically. Oh, the new child of blah and blah. You don't say the kid which happens to be have this and this and this and this and this inside. That's not what you say. That's not what you say.
Also, I think this has something deeply to do. I know you know this. I know you've done a lot of work on this, but also deeply to do with linguistics, with what we mean by communication. When we use words, when we say things, it isn't that there is a primitive substance to the words that we say. It is all made up by the ways they're being used and interacted and responded to. So, I mean, that's
exactly.
the view.
I think of all the sort of formalisms that have been developed. Mathematical linguistics a la Lambic and a la Chomsky and things like that. That's kind of the first incarnation of this sort of reasoning. I mean, one has to also be, I mean, Leibniz already had this view on setting up space-time. And to some extent, you could even say that Euclid already was to some extent thinking in those terms, because he described points. Like one way is to say a line is made up or in that way. Another way to say is like, I mean, I got 2 points and they're connected by a line. Is that third point also connected by a line? And if you look at some the way Euclid formulates things, some of that is there like this. Rather than how things are made up, it's about how things are related by lines and planes and stuff like that.
Exactly. He never says what a line is. He just essentially says a line is what 2 points define, essentially,
Yes.
uniquely, you know, and so it's all relational in this way.
Yeah, exactly. And then Leibniz followed this up by his view on and it was probably the first time he used the word relation in the way like space-time is set up. Of course, now there are very heavy proponents like Carlo Rovelli and Julian Barber, who push these ideas in very different ways, both of them, by the way, because whenever you're in a room with two of them, I had to, in more than one occasion, I had to separate them myself.
Bob, I don't know if you know, maybe Priya told you, but we had Antonio Vassallo in this seminar, one of Julian's younger collaborators, and Julian joined us as well, maybe 2 months ago, and we had a similar conversation around that. Yeah.
Okay. Okay, so now the thing is, this is very unspecified. I don't want to say abstract. I refuse to use that word. Unspecified. So you want to know what's in the boxes. I mean, this could be electricity devices, and then what flows in the wire is electricity. And I mean, at that point, you already feel that it's very unnatural to start, if you think of an electrical circuit, very unnatural to start thinking in how things are made up. It's really what flows to where and stuff like that. I mean, same with water, doesn't have to be electricity. You don't think, again, not in these reductionist terms. I mean, a computer network is, of course, computer science, of course, an example, which was really forced in terms of process thinking and forced in terms of like relations and interactions, because think about the internet. I mean, it's all about relations and interactions. So computer science, obviously, as a new science, as a fresh science, was able to embrace such a paradigm very early on. Okay, what does quantum fill the boxes with? Spiders. Right. Okay, that's mystic. Now I'm mystifying things, obviously. So To understand what a spider is, let's understand what a wire is. A wire is a thing with two endpoints, which are connected by the wire. And what can you do with wires? You can plug them together, which gives you another wire after you do that. And that's it. I mean, if you want to axiomatize mathematically what a wire is by its behavior, this is pretty much the equation you will write down. Now, what a spider, okay, here is a spider. Rather than two endpoints, it can have multiple endpoints, or one, or none even. What can you do with this spider? So I'm introducing now a new object, which is a generalization of a wire. Well, this spider, as it happens to be, if you connect them, they also fuse together into a spider. Like a wire, two wires fuse together in one wire. Same story. Of course, now you have to do some accountancy on the number of wires coming in and wires going out. So that's the slight adjustment you have to do. But anyway, what you see here is like a rule I impose, an equation if you want. So this is my first equation of this talk. If you plug two wires together, then you get another wire. For people who work in category,
Did 8 wires become 7 wires here?
oh yes, yeah, you have to count the inputs
Okay.
and the outputs. And if they're connected by 2, it's a different story. If they're connected by 3, it's a different story. It's just that the number of inputs have to be the same, 3 at the bottom. Number of outputs have to be the same, 4 at the top.
Oh,
I mean,
yeah.
from this, you have a very easy corollary that if you plug a bunch of spiders together and you plug another bunch of spiders together, if you count the inputs on the one hand and on the other hand, and the outputs on the one hand, on the other hand, and they're the same, then these spider webs will be the same. You can always fuse them to one.
If I think of this as plugging in, you plug one output of one into an input, one of the inputs of the other, basically. And
well,
and
that's
got
one
that,
way to
yeah.
think about it, but it's even easier to ignore that. Whether it's an input, I mean, I'm not going to go into that, like, but this is really a story about connectivity more than anything. And if you want to formulate this properly in, say, terms of monoidal categories, which is the mathematical counterpart of these wires and boxes, it's quite, you end up with pretty complicated equations in the end. You end up with pretty complicated equations. So that's the way you can think about it. But the easier thing is to just forget about what you know and just say, okay, we plug them together and they fuse. And the only thing you have to do if you're gonna if you're gonna translate this to a concrete setting like a quantum circuit, you have to remember what the inputs are and the outputs. You'll see this in examples. Now, for quantum mechanics, we need two kinds of spiders, which we color differently, one green, one red, for the only reason that when Ross Duncan and I came up with this formalism, I had two pens in my office, green and red, and it stuck. That's it. There's nothing more to it. Nothing deep. Nothing deep. Now, here you see another equation, and now you see the green and the red are connected. So the inputs don't really play a role here in the output. It's really what's going on between them. Okay, that's a good point. What's going on between them is much more important than for the equation than whatever the inputs and the outputs are. So what's going on between them is that's now two wires between them. Exactly 2 or 4, which is the same, by the way, or 6, an even pair of wires. And then they just vanish. That's the rule. They just vanish. I mean, this is not a quantum seminar. Otherwise, I could translate these two particular properties in Hilbert space, but I'm just going to avoid this now. So that's the idea. And okay, so important too. And now I can start doing calculations with this about quantum programs. So what is
you showed us 3 rules, right? Like I'm just counting. Just
really 2, really 2.
Right. So, Bob, is it okay to say for people to think of this as the two rules that you just said? If there is an odd number of wires between them, then they merge and the wire disappears.
No. If there is,
okay.
Here the number of wires doesn't care. So of course it doesn't matter because they just fuse together.
Right. So, but there's only one. If there were 2, that would be the. It's no force on you.
It's the colors. It's the colors that matter.
Oh, it's the colors that matter. Okay, very good. And so when the colors are different,
Same color fuses,
Mhm.
different color, the wires vanish
Splits.
if it's a multiple of 2.
Okay. Good.
I mean, if they would vanish for any wire between, then it would be completely trivial theory.
Right. Exactly. Okay.
Yeah. I mean, it's good to clarify this point. Thanks. Okay. So now we're going to start computations with quantum programs. So what is a quantum program? It's something you stick on a circuit-based quantum computer. I mean, I didn't want to specify this, but that's it. That's how it looks. So the way you have to think about this picture here, just forget about spiders now. These are 3 qubits, 3 particles, or three whatever. These are gates you apply to them. So this is a usual circuit model, huh? So these are 3 gates. We want to know how we can simplify this. So this is something you could stick on a quantum computer. Actually, this particular example, there's nothing much quantum about it. This could be just like a classical bits and stuff like that. And for particular choices of the green and the red spiders, which if you want to go to Hilbert space, would be for people who know that the Z and the X observables, these actually are C-not gates. These are C-not gates.
Yeah.
Controlled not gates. So we got like a bunch of qubits and a bunch of controlled not gates acting on them. And we want to know if we can make this simpler. Now I just said, forget about the spiders. Now let's just think of it as a circuit. Now we're going to forget about the circuit and think of it again as spiders. What's the first thing you do? I mean, you can tell me.
You can merge the similar
You know
colors.
that. I know you know that.
Irfan, you should answer.
Well, I mean,
You're putting me on
see,
the spot.
the ones of the same color are going to fuse together.
Right. That was the
They're
first one.
gonna, what?
That's the first rule. The first rule is this, right?
That's the first rule, because the rule also applies to that. It doesn't matter which color, same color, they fuse together. First rule, bang. Now,
Wow, nice. Irfan, your turn.
now which one?
Now the things between red and green, they vanish.
Yes, bang, they're gone. And I mean, I now bring in a sneaky rule, which it's like I said, spiders are generalization of wires, but now you see 2 endpoints, so it's really a wire. And that's it. So I just simplify this circuit. Very trivial calculation. The interesting thing is, what I just showed you is now the state of the art to simplify quantum circuits. This method.
Awesome.
I should say, this is not the full quantum language which I give you. I will mention something about that later. But this is really this method, like for very complex circuits, is the state of the art on how to simplify quantum circuits. And if you go, for example, to the ticket compiler, which was actually developed by Ross Duncan, who was my co-inventor of this language, that's what happens inside the compiler to simplify the circuits. This is what happens there inside. So this is not just like an easy way to do something. This is actually a better way to do something. And I mean, again, I can talk a lot about what's going on here and make analogies, but let's move on. I mean, I'm also.
I was just going to point out, this reminds me very much of the graphical linear algebra that Pavel developed, and
I mean,
about which is
the
as a
graphical.
plug. Yeah,
Okay,
he's going to talk about
well, I
it in
mean,
2
it's
weeks. So
the graphical linear algebra. Well, there's 2 things Pavel does. There's the graphical linear algebra, and then there is his work in like computer science, like how he represents lots and lots of computational processes with diagrams. And actually, the difference with this here is that the equations are pretty much the same, but they work at additive level. While this is multiplicative level. This is like times, while what they are doing is plus. It was very interesting, like Pavel never really I mean, I knew Pavel for a very long time, but I didn't really follow this because a lot of people say we can't understand this because it's about quantum. We don't bother reading this, blah, blah, blah. And then they posted the thing on Facebook and they say, hey, Pavel, do you realize that these are all the ZX calculus rules? That's sort of a technical term for this. And I said, oh, whoa, wait a minute. But the difference is they work additively. They work on matrices. Well, this is tensor-based. So that's linear algebra. This is multilinear algebra, focusing on a tensor. So that's mathematically the difference. But the equations are the same. Well, they're a fragment. They're a fragment of what we are dealing with. Yes, exactly. Okay. Now, let's go quite a bit more complicated as far as your Hilbert space formalism would be concerned. So one important thing in quantum mechanics is that you both have quantum and classical things going on. If I observe a quantum system, then I get classical data out. I get like a reading on a meter or a number or something like that, which is classical whenever I do a quantum measurement. And we want to now have both of these aspects, classical data, quantum data, in the same language. So here, this is a thing which goes from quantum to classical data. The input, now, what you see here is we represent quantum by 2 wires and 1 wire. So before I was representing everything by 1 wire, to make a distinction between quantum and classical, I'm going to represent quantum by 2 wires and classical by 1 wire. This is not some random choice. This just is exactly what gives you proper quantum mechanics. This choice, so it's so simple. It's a von Neumann implicit. I'm not going to go into that because it's not a quantum seminar, but implicitly in von Neumann's treatment of density matrices, this was there. This idea of doubling. For people who know how you represent the density matrix, is you take a bra and a cat and then you sum them. That's really the 2 wires here. That's really what's going on here.
Bob, mathematically, is this essentially logically equivalent to the fact that we need this to be over the complex rather than the reals?
Well, that comes in later. At the moment, it doesn't matter. But to do density matrices properly, you need complex numbers, otherwise you can't diagonalize.
What I mean is, yes, that's true. But what I mean here is that
implicit.
You have essentially 2 degrees of freedom implicitly. You have a phase on top of, like you have a, you have a higher dimensional scalar.
It's not really that. It's more that the density matrix is 2-dimensional, and a probability distribution is 1-dimensional.
Okay, I got it.
So this 2 wire represents the 2 dimensions. Like I mean, it's of the matrix. You can think of it as the input and the other wire as the output of a density matrix.
But the only thing that we measure is, some sense, their inner product, so that you can't have both information. You lose some information in the measurement process, is what essentially this is saying.
I mean, yes, that's probably a better analogy. Like, that's probably a better. But the thing is, like, a matrix, of course, has 2. I mean, it has 2 dimensions: the input and the output, and a map from a linear map from H to H. The space of linear maps from H to H is isomorphic to the space of the tensor product between H and H.
Yes.
That's what's going on here. So density matrix is from H to H. Here it's represented in the space of the tensor product, H and H.
2 vectors going into 1.
Yes.
Yeah.
Yes, that's really what's, I mean, in a sophisticated way, that's, what's the name? There's a name for this. If you do this in infinite dimensions, I can't remember it. Oh, whatever. Yes.
Like Adamar or something?
Can't remember it so long ago.
Anyway.
Hilbert Schmidt. Hilbert Schmidt correspondence. That's it. And so the top part, you have to think that's like probability distributions or something like that. And the bottom part, as I said, is like more density matrix flowing there. If you want to understand that. This is the thing upside down. For example, you've got a classical bit and you encode it as a quantum bit. So what we got now is, the description of a quantum measurement is basically by a self-adjoint operator, and then you take then use the spectral theorem to find the projective components, which you then use to impose von Neumann projection postulate to collapse them on eigenstates and stuff like that. That's all in here. That's all in here, built in. You don't have to know that. It's inside here. once you're going to start doing computations, all of that blah, 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 which I was saying, will be respected
Wow.
without knowing about it. Okay, so this is the opposite. It's where you got, like, say, a classical bit and you encode it in a qubit, which is like an initiation of your quantum state, say, in a computer. We can start doing calculations now. So you initiate a bit as a quantum bit, and then you measure it. What's the result?
Identity.
Yes, they fuse together and you get a wire. As simple as that. Okay, you encode a bit as a quantum bit, and then you do, this means measurement in a different basis. Well, a very specific different basis. Like position and momentum, say. One is position, the other one is momentum. What you get? There's no connection anymore, which means that there is no connection between what comes out at the top and what went in the bottom. So the top is basically randomness. It's just randomness.
Bob, is it useful to be, in fact, with this example, to be thinking of the two colors as basically being orthogonal?
Oh, not at all. That's wrong.
Okay. I got that from the book, but I just wanted more clarification
that's
about
wrong.
this.
That's wrong. Because orthogonal states are comparable states. They're part of the same basis, so they fit in the same color. This is the idea. I mean, I don't know whether I can show this with my feet. So you got one basis. This would be a basis which is such that if this is 0 vector, 1 vector, which is exactly in the middle, one basis vector and the other vector 2. So they are as incomparable as they can be. And that's mathematically a non-trivial characterization, by the way. One of some very big problems in just quantum computing mathematics is, for example, how many of these exist in a certain dimension. They don't even know in dimension 6 how many different exist. It's a very complex, complicated characterization in Hilbert space, but it means they're as far apart from each other as possible. The bases, not the vectors. We're talking about bases here. We're not talking about vectors. That's why. So that's a different property.
So we take it as a primitive in this algebra you're describing to us. That
Here
there
it's
are
a primitive. If you want to figure this out in Hilbert space, it's quite complex.
Right. But we only need 2 here. We don't need to know if there are any more.
Well, yes, we only need 2 here. I mean, that's again another discussion. But let's for now. Here we just have 2. Yeah. I mean, there in like real dimensions there are only 2. In complex dimensions there are 3. X, Y, and Z, like in just the 3. Yeah. On the block sphere.
So that means there are 3 colors, right? 3 colored, like 3 different colors of phi.
But again, that's a different discussion. In this language, you only need 2, and there are reasons for that I could get into, but it's not important. If you got 2, that's enough. You don't need anything more, it turns out. Okay, so these are more interesting example, different examples. You see now I've got this green dot with 2 wires coming in and 2 wires coming out, and then also another wire coming out. This means I've got a quantum system coming in, a quantum system coming out, and then some classical data coming out too. Which means we don't destroy the quantum system. After the measurement, it's still there. That's really what it means. So we measure, say, one property. Let's call these different colors properties. We measure one property, then we measure another property, and then we measure the first property. And the result is fascinating. The first time that you measure, say, property green, and the second time that you measure property green, the outcomes you're going to get are completely disconnected. They have nothing to do with each other anymore. Now, the way to explain this in usual quantum explainer is that the thing in the middle disturbs the systems. And it disturbs it by what's the projection postulate does and stuff like that. But you don't have to know about that stuff. It just happens here. So this is all the stuff the kids were solving exercises about, I should say that. So they were dealing with problems like this.
Nice.
Which are highly, highly non-trivial in Hilbert space. this calculation in Hilbert space is quite non-trivial. I mean, if you're trained in it, you can do it, but it's not so easy. Okay, now what I've presented so far is not yet the full language. This is not a language in which you can describe all of quantum mechanics, obviously, because there is something more going on. Now, the thing you need is you have to decorate your spiders, and that's where more explicitly the complex numbers come in. So basically, you have to decorate them with phases. Now, when we first wrote this book, I told my co-author, Stefano, we don't want to use any mathematical numbers or anything like that, so we're just going to use phases of the moon. After 10, 20 pages of drawing phases on the moon, he was about to kill me. I said, okay, let's move on to just writing angles. And the thing is, I know in the UK, children learn angles at age 7. So it's not too far-fetched. It's not too far-fetched.
Mm.
So basically, you have to decorate your spiders with angles, and what happens when they fuse is these angles add up. So that's
Nice.
That's like it's an extension of the rule number 1.
Mm.
That now there can be these decorations which add up. Calculation-wise, it doesn't involve any complexity rise or something like that. It's a straightforward thing to do. Now, this is different rule. I don't want to go into that too much. It actually tells you, suppose that you've got a square of red, green. Suppose you got a square. What can you do with it? Well, you can basically write it as the thing on the right. So instead of you kind of get rid of the square. As it turns out, this essentially implies the rule we had before of the sort of 2 wires vanishing. Don't want to go in details. You find these all in the kids' book, extensively explained. The reason I give these 2 rules essentially is because of the following theorem. Von Neumann's quantum language, as far as you can produce any equations from it, so all equations you can derive in von Neumann's Hilbert space formalism, you can derive with the rules I gave you. So it's a genuine substitute of Hilbert space, quantum mechanics. So it's something I even didn't believe myself when we were doing this.
Yeah.
So it's something I didn't believe myself, neither did my Ross Duncan, who came up with the spider language with me. Neither of us believed this, that this would even be true. But it turned out it's now there. So it's called completeness. So what it means, so there's 2 things implicit here. This means anything in your usual quantum language, you can describe, not just describe, so, and that's universality, but any equation that you can prove between those things, you can also derive with the diagrams. So it's a genuine substitute. And now in quantum computing, it's very prominent just to solve practical problems. Many practical problems. I mean, especially for people working with photonic quantum computing and things like that, they use this as their main language now.
That's wonderful.
Because yeah, it makes impossible things possible to compute, basically, and more intuitive. And even if you work with computers and you want to code things, this actually is a better way to even work with computers and code your problems. Okay, I think I run out of time. Yeah, I'm pretty much at the end of my talk. I just wanted to, because people were
Yeah, please, if you would like to.
I mean, I can go very quickly here.
Yeah.
So because linguistic was mentioned before, I mean, I think this is a nice thing to quickly put down. So when I was giving a talk about this kindergarten quantum mechanics paper in McGill in Montreal in 2005, and this picture on the top is like a diagrammatic sort of example of how you basically describe quantum teleportation and what it does. So I was giving this talk in, probably 2004. This was even before, I think, 2004. I was giving this talk, and then one of the most prominent mathematical linguistics in the world was in the audience, who's a very good friend of me, by the way, was a very good friend, Jim Lambeck. And when he saw this picture of teleportation, he says, "Bob, this is grammar." So in 1956, Jim Blomberg wrote a paper, The Mathematics of Sentence Structure, and from there on, this was like one of his many fields he worked in. So he formulated what it means like for sentences to be grammatically correct with the mathematics. And this was already hinted at by Ted. This actually is very relational. Of course, it's about relations between words and things like that. And then he realized that the formalism was presented for things like quantum teleportation was exactly the same as you use to relate words in sentences in order to understand their grammaticity. So that was interesting. And then the reason I ended up like spending, ended up in quantum industry and stuff like that, is that we used this correspondence between quantum and language to basically start doing quantum natural language processing on quantum computers. So we basically did our first quantum natural language early 2020, I think. For the first time, we solved the problem on an actual quantum computer. Well, some question, well, easy problem, some question answering on a quantum computer. And then we developed this whole line of work on quantum natural language processing, which was entirely a new field, of course, by then. I don't want to go into that, but this is just such a nice thing that by putting quantum mechanics in a different language, it also makes you related to other fields, like linguistics. And the idea of the underlying philosophy there, the relational philosophy, is really the core thing here that's going on. So we could directly translate language into quantum circuits very easy, and the relational information we got made something like language processing, which usually very highly data driven, much less data driven, because you can make use of the structure. Now,
which parenthetically was exactly Chomsky's hope and goal and the big challenge, right?
Which one? What, can you repeat?
Chomsky.
Yeah.
I said Chomsky's goal originally was how can language acquisition in humans be done when initially he thought it was very data driven, right? Like we had to have all these examples to learn from, and he said no, it can't be. It has to be more structural, more.
Yes.
They have to, you have to rely on structures that you learn, not the examples.
Exactly. Yeah,
So,
yes, I agree with that. Yeah. So does anybody know the guy with the beard is? I think many of you know him, but you probably don't recognize him. Brian Eno. Does anybody know Brian Eno? So that's Brian
the
Eno.
musician. Yeah. Wow.
I mean, it doesn't look the same anymore in the early 70s.
Yeah, I was going to say, wow.
No, anyway, so what he's looking at here is a book. I mean, these are two of my collaborators in the quantum music next to him. I was in Australia at the time when this event happened. And he's looking at what's kind of the first compendium of quantum music articles, science articles and something like that. And he was particularly looking at a paper by ourselves in there, which is a quantum natural language processing approach to musical intelligence.
Musical intelligence.
Musical intelligence. So we basically took the thing I was just talking about, which came out, this correspondence of quantum and language. And what we did is, language is, of course, much broader than speech. So music is language, and you can replace like linguistic grammar with musical grammar. You can replace linguistic meaning with musical meaning. That's exactly what we did here. And then basically came up with a sort of quantum approach to generating music. And we were the first to then produce basically a piece of music generated by a quantum computer. And this ended up #1 in classical charts. So we started with the pictures of quantum, then we went to language, now we're at music. So just to see how having the right language for things, of course, music is incredibly relational, of course. So it's the same thing again. There's a recent paper, if you're interested, in where Rakat Abdizagin is one of the world top composers and musicians and performers, basically used this spider language to start to develop a new language for music too, which is on the nose, where the relational aspects of music are visible and not hidden or behind the usual music notation, which is not at all relational. The notation, I'm not saying music is not relational, but traditional music notation is completely non-relational. And then I mean, these are some examples of how it looks, and you see between the different steps, you see connections of things that are related, something like that, and we even different colors come in the way we are doing it. Anyway, so this is my.
So do you mean like you can? Sorry, Bob. Do you mean like you can write the entire composition in ZX, like in the Spider language?
It's well, we're just starting this, but you can do things which are very hard to write down in usual notation, in this notation, and this is a very this is actually a piece of music what you see here. I mean, I can't explain what it is, but it's something myself and him performed together. We've done it. We tried it out twice, once in Vienna, once in Berlin. And we'll be playing next Sunday, not this Sunday, next Sunday here in Oxford. He just arrived from his plane. He just wrote me from Kazakhstan. So he's very, he has a very interesting book which recently came out, Quantum Mechanics and Avant-Garde Music, which takes a very different perspective, which takes a much more historical perspective, but is getting very lauded. I mean, they call him the Kazakh Mozart, or the Mozart from Kazakhstan or something these days, because he wrote his first symphony when he was 10, something like that. So he's a bit a crazy guy. So like I said, I developed a quantum guitar, not going to go in details. And now I have to run away very quickly. Okay, now you can watch the video, as already was said, quantum guitar. And I have to run away quickly because I've got a lot of work to do, because I've got these 2 concerts coming up next week. For the first time in my life, I'm going to be part of a symphony, you know, playing in a symphony. I come from an industrial music background, so I'm not usually playing in like organ symphonies. Like I'm not used to play together with like a cathedral organ and stuff like that. And then the second concert is in part like what I was just saying about. We each play parts in a bell pair, and then we measure each other and stuff like that. So that's the sort of thing we do. Anyway, that's the end of it.
That's amazing. Let's thank Bob. Do you time for a few questions, or like when do you have to, like we could stop when you want to leave?
I have to be at 7 in the city center to meet him, and it's now 5:45, so I've got time for say 15 minutes.
Okay, great. Thanks so much. That was a very inspiring talk. Thanks a lot
Thank
for
you.
all
That
details.
was fabulous, Bob. Thank you so much for taking the time. This is fantastic. It fits so well too with the various things we've been trying to do. So yeah. I'm gonna certainly be in touch with you regarding my
That remind me, we met
Yeah.
in Oxford at a consciousness
a
conference.
couple of times. Yeah, a couple of times. Yeah, maybe a couple of years ago last time. But yeah, I teach at a school in California at a kid for gifted kids, and I teach a QIC class for the last 5 years. That's very popular. I've even done some research with some of my students and people like Tai Danai and some of her
Keep
collaborators
talking, I'm
on
just going to
QNLP.
take something. Keep talking.
Right. So I'm very interested in. It's been a goal of mine to incorporate the book with Gojozo on as the main textbook in my class, like moving away from the traditional ones to use this. And I've used examples in the past, but I think I want to go full hog and use the book itself. So I'm going to be talking with you, I think, emailing you for advice and so on. But this is a fantastic initiative that what you're doing. The other thing that it reminds me is of something that Richard Dawkins said at a TED talk in the early 2000s, probably around the time you started working in this. They're speculating what would happen if we taught young kids relativity and quantum mechanics through games, so that they would learn to think in these ways more naturally without all the machinery that we end up teaching them, after the fact. And he had this very interactive sort of gamification in mind. And I was fascinated. I've been fascinated by this ever since I heard it. And you seem to have taken this to another level. I mean, to actually make it happen. This is fantastic.
Yeah,
Thank you.
I think Terry Rudolph, he has a book, Q for Quantum, I think, which is a little bit more sort of in the idea of like explaining it by games. But of course, it doesn't take you to the full quantum formalism in a way that you could actually start doing research cutting edge with, which I mean, like I said, this is not just an educational tool. This is now widely used in industry.
And I think this is fantastic. This is what you just said is a main thrust for the Relatorium seminar, for our work, with Priyaa and my group. My group is exactly that enlarging the language by which we represent mathematical ideas is going to be essentially useful not only for more inclusivity. So in other words, when we're talking about compassionate math, it's not just trying to be kind to other people, which is by itself very good, but we're also being kind to ourselves, because that's the way we understand our field better. In other words, it's also at the cutting edge of research. Teaching and doing mathematics isn't, and in this case, physics and so on, it's not a separate enterprise like people have come to think. We have to, in some ways, return back to an earlier conception where the talking about it and teaching it and learning it and doing it is more a continuum. And I think this helps. I mean, I'm very heartened to hear that this is a full-blown, complete language for quantum mechanics, and that in fact people are using it to come up with new ideas in quantum mechanics.
Yeah, I mean, there is a more recent historical story there. Of course, there was Hilbert's program, and then you got Bourbaki. And then Bourbaki, of course, had a very particular view on how mathematics should be presented and taught. And he was like, no examples, no illustrations. And so even to start thinking in terms of coming up with pictures or anything like that was complete taboo for a very long time. And then another, I mean, it took a very, I mean, it took a very long time to convince mainstream quantum computing community of this. Very long time. Well, I mean, it mainly only took off when industry, like companies like IBM, start to advertise it, use it. I mean, and things like that. But the sort of academic community didn't like it. Why? They still come from this sort of macho style Bourbaki tradition, white male macho style Bourbaki tradition, about showing off how smart you are. The idea that you turn things easier was completely against the spirit of things, so to say. You know, the sort of show of I'm solving so many complicated problems, blah, 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 blah. Look, and it's part of mathematics. Oh, he solved this very difficult problem. Oh, he solved this very difficult problem. Oh, he solved this very difficult problem. That's sort of the spirit, which in part was induced by Bourbaki. Because because they also had sort of this state. So when these people were asked, what is good mathematics? Good mathematics is what good mathematicians do. As in ourselves.
Yeah.
Finally, I have to jump here. I'm about to explode mentally.
Great, yeah.
I'll try to be brief. Thank you. I'm not a mathematician, so having a prospect of understanding something understood commonly as complex as quantum mechanics in this way it's so exciting. And it also scares me, because the question is, what happens if I still don't get it?
I mean, that's not, I mean, let me comment, just that you don't get disappointed if that happens. Like I said, the 15-year-old did better than the 17-year-olds. And then a lot of people of the mainstream quantum computing community had difficulty understanding this. And some of the arguments, why should I learn something so totally different, new? What can I do with it? And spend a lot of time learning it. Now, the kids did it in no time. And the problem with people who already know too much is they want to translate to what they already know. Translating this to Hilbert space is highly non-trivial. It's not the most obvious thing to do. If you give it as an exercise, like you would give this language to like, say, a professional physicist, quantum information person, they never seen this. Okay, now translate this to Hilbert space. They would have a very hard time doing that.
I just must say this. The implications of what you're saying have global ramifications when you're looking at matters of inequality, injustice, and so on and so forth. Let me try to connect these dots. When you talk about a fundament as being one of relation versus substance, you're ipso facto talking about social inequality, bias, and so on and so forth. When I look at the global map of where this language is being taught, and I look at, well, I just saw 3 countries, Ghana, South Africa, and then Australia. Those are locations whose history of oppression of indigenous people is well known. You're teaching at a primary level a language that says that who and what things are matters of relationship rather than substance. Social injustice globally is based on the quota that you are a substance. And once you define that essence, that's what you are. It's fixed, it's final, and you're doomed and damned. So now you're talking about a way of totally reconceptualizing who people are in the world, what they are made of, and how do you make sense of that making. My God, that is so profound and so exciting. One more thing, and then I'll stop. You mentioned briefly something about your concerns regarding trauma and teaching this language to such young minds. And could you say a little bit more about what your pedagogical concern was? And when I said I was going to stop, but I'll say one more thing. Where I see a danger of trauma for young people is the upside downness of your language. Because if you're teaching people at 15 that when you look at a human being, you look at how you relate to them rather than what you were told by your parents and your community, their substance and essences are. If
Yeah,
they
okay.
stop starting.
Okay. Well, then I thank you for everything you said. Thank you for everything you said. So I'm trying. I want to comment. I think the second one was the easiest to answer. It was not my concern. It was the bureaucrats' concern and the system's concern, and it's an understandable concern from their perspective. Teaching quantity. So it was just like overcoming that. So we actually had some. I did some. Trials with a few people from France who did like placements with me, and they all did really good, and that helped like in convincing that this wasn't a problem, like, and with some witness statements and stuff like that. So that was okay. The first one is probably the longest question to answer. What was the third one again? I forgot. The last comment.
I think it was to do with his conception of the upside downness of the language being potentially traumatic. In other words, that the kids are seeing something which contradicts what they've been taught by everyone else before. Am I right, Grady?
Yes, that's it. I lost track of the count. I don't know what was first or third. My loading, and it was hard for me to sequence. It all sort of comes together.
No. I remember you were mentioning like 15-year-olds. They don't care about their parents. They care about their friends. That's what you said. So no, the first one is very deep, and thank you for bringing this up. So I mean, the slide is completely outdated, and then since you mentioned a friend colleague of me is now working with indigenous people in Canada. She when she immediately saw that, she started like pushing it there, and so a lot of these things are going on. So it was the first time when we started doing this thing, my first reaction was, we need to go to Africa. I mean, the point you made about inequality, as I didn't realize this so much. And I completely take it on board, by the way, what you just say is told. Thank you. My thinking was more like cultures in, say, Africa and other parts of the world, they're very different. They're not so indoctrinated in Western like reductionist thinking. So my feeling was that people in, say, in Africa could actually be much better at this, and they could actually outperform Western thinking because they don't have this sort of reductionist foundation to start with. So
and also in African indigenous cultures, the mythic understanding of the world tolerates the merger in the sense of contradictions. I mean, in African American speech, when someone looks at something that is just amazing, awesome, they say that's bad.
Yes, yes, exactly.
Song by James Brown, the icon that was called Superbad.
Yes,
So
yes, yes.
So you're absolutely right. The indigenous conceptual framework is much more open to just throwing out the law of non-contradiction and the excluded middle, because they live in the middle. John Coltrane said that he wrote his music from the middle. Middle chords. He took the extremes and then he wrote and composed from the middle. The transformation of our world is going to be just like what you described. It's going to be out of the view of the main political drama. It's going to be in an incremental way, and it's going to be done passionately. When I took a peek at your music on YouTube and I was trying to put it all together, and I said, we live in an amazing world, and the pace of change is really escalating. But how many people who are in the activist realm are aware of the burgeoning that you're describing here? This is truly atomic, nuclear, in the biggest and best way. So thank you. My God.
Yeah, so I mean, one of the things which I'm planning to do in the near future or the next year or something like that is take a lot of time off, like and write a book exactly about the kind of things and the sort of where this discussion is going to, like this relational thinking and all of that that comes with it. It's not, I mean, if I don't do it now, I'm never going to do it. And I thank you, and thank you for that input on. You're perfectly right. All the sources of discrimination are about atomism and stuff like that. How things are made up, all of them.
I mean, people are being murdered because of their perceived substance.
Yes, that's a very powerful statement what you just said. Yes, thank you for that. That's in. But yeah, so I mean, that's what I'm gonna do in the next year. Write a book about all this stuff, because otherwise I'm gonna. I mean, you know, I've spent, despite the fact that I like thinking about these things very deeply, I developed that. I've been in very high profile position. I had like a 50. I built like the biggest quantum group in the world at Oxford and so on. So I spent my life mainly doing management, besides developing all this stuff. And then the same the last 5 years, where I had a big group in a quantum computing company, which was all, we did cool stuff. We did all this cool stuff, but I need time for this sort of things, for this sort of discussion stuff. I write it down.
Thank you. Thank you very much. Thank you.
Did you perceive any difference in how like different cultures respond to this material, Bob, like across the world?
I mean, whenever I gave talks, like this talk, for example, I gave a talk for like, so the Pi Day more broadly within Africa. I mean, of course, as many things, this is like organized by South Africa, because they're the most best placed for that stuff. Like, I mean, and I mentioned something like that, they all completely agree with me. Like I said, the first time, like a person who was working within the indigenous community and is also like in charge of a tech development in Canada, one of the high people in tech development in Canada, she immediately went for this to actually start teaching and get programs with the indigenous people. So yes, I immediately get this reaction from pretty much everywhere.
I think we have to put you in touch with David Stern, in case you probably don't know him. He's someone I met at Topos last summer, and he's talking in about a month here in this seminar, who is a Brit, a mathematician, who basically heads a nonprofit for educational innovation in Africa. In fact, he's in Africa right now, and he does a lot of outreach.
Is this AIMS? No.
No, I think they have a connect. I think it's ICERM or something like. I forget the initials, but I will send you the information. He would be very, very interested in what you have to say about it.
I mean, the thing for these things is just manpower, because it's
Yeah, indeed.
I mean, part of the problem I had in the past Like, I mean, I was at a quantum computing company, and it's very hard to get any sort of philanthropic funding if you're a very rich entity for this sort of thing. So, so I mean, I need a bit more space to develop this further, and some more formal initiatives are now being made, and we need just to expand some sort of network or whatever. Or so what's going to happen is, like, FQXI is going to put all their weight behind this now in the very near future. So they're going to release all the videos and all of that, which is helpful. And I think it also needs a commercial component, unavoidable, that there will be some sort of richer people, like executives, who also want to learn this. You can take money from them and then use that money somewhere else, you know. I mean, just practically, I mean, I think this may be necessary because it's hard to change the world. It's hard.
Also
It's harder to change science because science is such a slow-moving, conservative entity full of egos, and
right.
very little gain. One of the things Kissinger ever said, I mean, I don't like him, was like, why are people in academics so bitter against each other? Because there's nothing to win. There's nothing to gain.
The pie is too small.
Yeah. There's no pie. There is no pie.
There's no pie. There's another connection, and I'm not sure if he got in touch with you, as a Italian artist, basically, called Paolo Cirio, who visited us here. I recommended that he get in touch with you. He visited us here at Topos, and he met with a few of us and had interviews. He's trying to put together, he's a hacktivist, basically, but he has basically a contract for museums in Europe to put up a display or some kind of exhibition relating to quantum, basically emerging quantum language, how it's relevant to the human experience more broadly and how people conceptualize it. He was very interested in notions, quantum use for cryptography or for this computing, and in general, how it's changing the way people think about the world. And I think he changed his itinerary to include a stop at Oxford at some point in the fall, I think. It's anyway, there are interests. This is to build on what Grady was mentioning, that these notions that have come from technical, to begin with, from technical needs, like how do we describe quantum mechanics in more simpler, more effective ways, but have spawned ideas that are more broadly relevant to the human condition today in ways that, we're just beginning. Even you, who are an expert, obviously have been thinking about this for so long, you're still beginning to understand and find time to devote to. So,
I mean, one thing I forgot to say, and I want to comment on Grady's, the political dimension I saw was that if you see how people build arguments in the world, politicians and stuff like that, it's all still tracing down to propositional logic a la Aristotle. And that's a way you can basically, you completely ignore the environment when you make an argument, because it's about isolated systems, because it's about how systems are built up. And so all the arguments people use in the world now are so flawed when you put them in a social context of humans, because they just take the wrong framework to start reasoning in. So that's the thing I always, and I wanted to write about too, that a lot of the misery in the world because of disagreements and stuff like that all goes back to sort of Aristotelian reason. Don't get me wrong, I really appreciate Aristotle a lot. I got a lot of respect for him, and he would probably not be saying what he was saying then now. He would have been saying, but everybody's still following that sort of logic. What people call logic is Aristotelian logic. That's not the logic of the world. It's not. It was a big progress at the time, but it's not.
Yes. Yeah. And in our work here, certainly in the oratorium and compassionate math, we want to foreground logics as a plural, just like maths is a plural, it's irreducibly plural, that we do need the multiple perspectives. There's always choices.
I think that's what the logicians were doing, like with like model logics and paraconsistent logics and stuff like that. But it's still, as the Aristotelian template, of like talking about an isolated thing.
Yeah.
There is no relational logics.
Yeah.
They're not. They basically,
Well,
you can have relations between logic, but that's the wrong aptitude. The
so
relations confer, not the entity.
I'm sorry that Nathan Hayden, our collaborator, had to step away, obviously, but he, in fact, is a computer scientist and philosopher who specializes exactly on relational logic. He would maybe, in fact, he uses diagrams and basically Persian.
The first
on
person,
this. So,
Peirce is the
yeah,
first.
exactly.
Peirce is the first philosopher who started to go in that direction.
Yeah.
Irfan has a question.
Oh,
Irfan?
yeah, I wanted to ask you if you could say more about what Leibniz's conception of space-time was and how it was more relational.
It's similar to what now Rovelli and Julian Barber and people like that are saying. There is sort of no absolute space. Like you got an object in space. If you're alone in space, there is no notion of position or momentum. There is nothing. If there is a second party and second entity, okay, new properties emerge. Like there is like this, how far are we from each other? When a third one emerges, a new property emerges. When a fourth one emerges, a new, and then you see it's the entities in space that and it's about where you are relative to other people rather than where you are. So we usually start defining space with coordinate systems.
Mhm.
There is no
Exactly.
coordinate system.
Right. It's like the desire to reformulate physics on configuration space rather than on physical space. So just in the relative, positioning of the different components. It's still not fully. I don't think even Julian and Carlo would think that they're achieved it. Even certainly Leibniz did not achieve it. Mach tried and later and didn't fully achieve it. I mean, to have a fully relational idea is aspirational at this point, right? Like
Yes.
we come up for physics.
It's more considered as a perspective at the moment than.
Exactly.
And of course, I mean, Carlo did take it up and then try to make a relational formulation of quantum mechanics, but I mean, even he would say that I got much further in that himself. I mean, we are close friends, and we have been in projects together, which I couldn't put enough time in at all for the last 10, 12 years. Like we've been in Templeton projects, very big one, networks, maybe the quantum information structure of space-time stuff, but I never had enough time to go into that. But yeah, it's.
I'll ask this question, Bob. I'd love to know if either your work directly or your broader conception of this type of reformulating physics using diagrams, using this relational thinking, how you see it being related to the constructor approach, like Deutsch's. And,
not going to go into that. Not going to go into that here. We wrote a paper about that.
Okay. All right. Okay. Because I haven't gotten a good idea from them either. I mean, Chiara, I know personally, and I tried to pin her down on that. And, it's slippery, let's just say. I would love to understand better. But anyway,
So we have got a paper about that. I think a process theory view on constructor theory. That's the title.
Okay.
And that's it.
Thank you. Thank you. Well,
okay, I have to run now.
This is awesome. Yeah,
let's thank our speakers.
Awesome.
Thank you so much, Bob, for spending extra time
everybody.
with us. Yeah.
Very fun.
Bye.
Very fun. Bye-bye.
Cheers.
Where's my